So for the remaining 15 minutes also, I'm really gonna have let's go down a bit on mathematics to see how Nash proved the existence of Nash equilibrium in the finite games. When I say finite games, I mean the game that we define, we have a finite number of actions, we have finite number of players. We play this strategic form game, which can be written down as the the form, normal form, as we written in the tables, right? It could be the high dimensional table if you have a multiple, if you have more than two agents, more than two players. So in his theorem, Nash said that every finite game, as we defined previously, has a mixed strategy Nash equilibrium. He didn't really say, whether that's unique, right? It might be the case that we have multiple Nash equilibrium, Libra, as we can count it. But he basically, this theorem tells us at least there's one mixed strategy Nash equilibrium. This is very important because, as I said, knowing this, and then you would perhaps really try to find it, but without knowing it, there's no point of finding it, right? So I think this really solved at least the first fundamental problem, the existence of the concept that he defined. So once you got that, is really the next question is try to find this equilibrium, right, or equilibria. So let's. Okay, does anyone have a question?
Does anyone have a question? No.
Okay, please, mute if you don't speak. So this let's draw down to some math. Okay, so let's say sigma I. We're using the capital sigma to represent the set of probability measure over the pure strategy action set. So in other words, you can consider sigma as a probability to choosing one of these action. So for example, if I have two actions, the sigma would be just simply one parameter, right, from 0 and 1. The probability choosing one of the actions, the other is basically this 1 minus sigma. All right. The lowercase sigma I is the specific case of that. Sorry, the sigma I is that we denote the set. Okay, that's basically a choice. So in this case, it's the continuous number between 0 and 1, include the 0 and 1. Okay, and the sigma I is the instance of that. In other words, it's a mixed choice. The lowercase sigma I is a mixed strategy. The player I is choosing. Okay, the joined mixed strategy is a sigma that is a sort of a product of that, in the sense that we're gonna looking at all the agents, right, all the players, and then the set from all the players, then we construct this sigma, right? This is a joined mixed strategy. So in the two agent, two action case, you got a P and a Q as we sort of illustrated. So we're using this sigma minus I to represent these other agents, our other players, apart from item I, because in some cases that we might looking at multiple agents, go beyond two agents. We might have an agent at 1 and 2, maybe 3, 4, 5, so on and so forth. When we see agent I, and then we use notation minus I to looking at all other agents or players beyond this particular player I, agent I that I mentioned. So then sigma, lowercase sigma minus I is the mixed policy of all these other players apart from player I. So with this mixed strategy, and what we can write it down is this expected utility. So this expected utility is not dependent on the pure strategy anymore. It's dependent on the joint, the mixed strategy, which is a sigma. Okay. Then of course for each of the players, then we have their utility, right? Payoff. We're using index I here. Is that clear? Okay. So then we can using this to sort of redefine Nash equilibrium as the case that we got this sigma star is a Nash equilibrium that in the sigma star, the utility would be higher than any alternative choice if these other players play their mixed strategy in the Nash equilibrium. In this case, is sigma star minus I, denoted as. So in other words, we can think about this as sigma star is a sort of a best response. It's a set of best response of each user, right? As we said that it's each one in the Nash equilibrium, it's that I best respond to you, you best respond to me. So we can, instead of doing this jointly, we can do in a separate way. Is that I got this sigma star I. If I were in the Nash equilibrium, I would always belong to the best response. Okay, which denoted as a function. Let's say we did not function. Sorry, we denote mapping. This mapping is called correspondence mapping. Between, let's say, input is the the set of mixed choice, a mixed strategy from other players. Sigma star minus I. I think I'm gonna using this pen. So basically this, okay. And because these others play this mixed strategy, this is one of my best responses. So the reason I say this is not a function, because if it's a function, this is just have one value. I will write down equal here, but this is sort of include, meaning that the output of this correspondent is actually a set. So think about this B as a mapping from set to set. So the definition of a correspondent is that a two set, right? So in other words, that this correspondent is that I input a set and I will output a set. Would that make sense? And so, yeah, so let's here have a formal definition of this best response correspondent. Is a best response correspondent of player I, right? Given other players play the strategy sigma minus star. So let's check whether you already got a few questions. Is sigma a sigma algebra? Good question. So I try to avoid using this sort of measure theory or probability theory for that. I don't think it's an algebra sigma as we specified, but you can define it from probability theory. But I don't think we need to go that just yet. For now, you just think about this probability measure, right? Because in probability measure, obviously, is a subset of that. Subset of that, but without confusing this notation, I try not saying that. So let's go to next. The correspondence B, as we defined, as set is sort of a set to set sort of mapping. Is for all the sigma here we have. Is that we can sort of put them all together and write it down, say we got, sorry, I think we got this for the individual user, but we can put together, define the correspondent jointly. So the joint correspondent, best response is that are defined as a vector, okay? And this vector is basically compose each of the best response. So the best response is defined as before. So in other words, what we're doing here is to say, okay, the how can I write this? Is that, okay, I got this Qi star play in the equilibrium, right? And based on this, the best response for others is this. And this is the mixture sort of strategy from others. And because based on this, and this is my best response, okay, for player I. And this is the best response for all these other players, condition on that I'm playing this sigma I star. So you can then think about this as a kind of mapping of this function, okay, kind of mapping, corresponding mapping of, you can think about this, because this input and output, they are in the probability space, okay, as we specified, right? They are, let's say, for now, you just consider this, think about it as a, to without go to this sort of a general setting, to help you sort of think about this. Think about this as a sort of a P and a Q as we define it, right? And this as we define it, Q as well, but with a different value. Let's say with a different value. Then this B function is basically taking, okay, P and Q. Sorry, I think I think I'm right. PQ, and do this mapping and forget about this. You can just for now just forget about this sigma. This include kind of just think about this as a equal, and then you got this sort of a solution which is sort of a Q P. Okay, I write in a different order just to reflect that the P is best response getting Q, okay, and the Q best response getting P. It might be the case that you got a different value. So I'm using this prime here to say that just have the fact that they have a different value. But this basically try to say is that if the Nash equilibrium, so basically if you have a best response to this, it's not necessary to be Nash equilibrium, right? Because that my response to you respond to me, and then you apply different, you have a different best response. But it might be the case that in the Nash equilibrium, because nobody want to deviate from it, and the input will become the output. So in other words, I have this, sorry, I think you guys, maybe I can take 5 more minutes of your, try to finish off this. So you got this P and Q in the Nash equilibrium. Then you can immediately verify this P and Q would certainly hold for this. It's because that nobody want to deviate from it. This P's best response is Q, and Q's best response is P, right? So think about this, is that you basically have this sort of a B correspondent. The input and the output is the same. In mathematics, that is called fixed point of the matching. Because why they call it a fixed point, you're not going to change anymore, because you put an input and output input, and they won't change. Because think about that in these in the learning, and when we're talking about this Q learning and later on, you can find that they're all about a fixed point. When they want to try to prove the convergency, they're all about sort of whether there's a a fixed point or not in the end, because all these algorithms are working on an iterative fashion. When they're working on an iterative fashion, the fixed point is this very nice property, because you have this iteration. The input become output, output become input, then eventually will converge to the fixed point. Because in the fixed point, and you are the best response to me, and I'm best response to me to you, and nobody want to deviate from it. Any kind of fixed point. So if you write it down in this B, B correspondent setting, the input is your mixed strategy, output is your mixed strategy. And as long as you can prove, okay, this B correspondent mapping there exists a fixed point, then by definition of a large equilibrium, this fixed point is large equilibrium. Therefore, you proved, right? You proved the existence of large equilibrium. So just try to summarize this logic here is that we by definition we define this best response mapping by this correspondent P. Okay, so this P is input is a joint, policies, a mixed strategies, and output is a mixed strategy. But if this correspondent for this function there exists a fixed point. So in other words, the fixed point can be represented by this, that input is the same as output. Then we call that a fixed point of this correspondent. And therefore, by definition of a large equilibrium, and also because it's a best response to you and your best response to myself, and this fixed point is large equilibrium. Does that make sense? So in this Nash original paper, he makes use this one of the fixed point theorem. So this is extended Kakutani fixed point theorem is the extension of original fixed point theorem, because original fixed point theorem deal with this situation where you have continuous function, and here is Kakutani theorem basically dealing with a set valued function, which is sort of fit our case. So basically, this we're not going to go through this fixed point theorem, but rather from this based on this theorem to really prove the existence of large equilibrium. So what we really want is that we need to solve this set, right? This action set, mixed action set, sigma, and also this best response function. If they follow those four conditions, then and then basically this mapping has a fixed point. Therefore, the existence prove the existence of a large equilibrium. So that's the logic behind it. And let's go through each of the conditions. So before that, we can looking at this. What do we mean? This this set, this mixed strategy set. So if you think about this strategy set, we can take a looking at this example. You got 2 agents, 2 actions, a normal phone game, and you can write it down this sigma as their mixed strategy, and you can write it down. I have this 5 out of 6 probability gonna play U, and 1 out of 6 play D. So you can actually base this to write down this best response correspondence curve, right? So for example, this player 1, right? You do this 5 out of 6, and this opponent is y-axis, right? They can basically, this is their best response. So initially is 0, and no difference between them, right? And y. So equally, the red is the curve from player 2, and you can see the best ones. Initially is 0, and no difference in the mixed strategy, and same. So therefore here, if you look at here, is Nash equilibrium. Okay, so this is best response and curve, and also this space, the set space of, you can consider this just as capital sigma, the space here. So then it's easy to really see that this set is compact. It's also bounded and closed. So it's bounded because it's simplex, right? It's in the probability between 0 and 1. So it's bounded. It's closed because it also includes 0 and 1. So it's bounded and closed, therefore it's compact. It's also convex, and in the set is convex is because any link with this, if this guy in the set, and anything between is also in the set. So this is also convex. And the condition 2 is that the B mapping is non-empty, but it's quite clear that from this illustration, you can always have the best. You can always have value. You can always have value to looking at the best response. So this is the non-empty, and the last bit is the convex. So what do I mean by the convex valued correspondence? This basically means that for any sigma, the output, the set is a convex set. So this can be easily proved by thinking about, say, if these two are belong to this best response set, right? Given any opponent's play they got, and they can immediately write it down this, equality because of this definition of Nash equilibrium for any tau, right? Because this equality holds, and then you can actually write it down. Adding them together, you can basically add it down, like this. And you can make use of the linearity of the utility function, and you can put this lambda into it, and therefore this guy become the best response as well, and therefore you can prove that this is also in the part of this best response set. Therefore, prove that indeed is convex valued. So the last bit is this has a closed graph. So the graph of the function is basically a joined sort of set, a Cartesian joined set of the input and output. And the closed graph meaning that in this particular case is meaning that if I have a sequence of this pair, converge to X star, Y star, and if this sequence are all belong to the Nash equilibrium. In other words, the relationship between X and Y is they are as a best response to each other. Then they will show that the converged ones also is part of this best is part of this best response set. So you can think about this. You can visually see this is that if this converges to this point, and this point is certainly, if all these things belong to this best response set, and this point also belong to. So that's basically what this condition says. So again, this can be proved by contradiction. Given the limited time, I think I'm not go through this, but you can have a look. This is quite clear actually here, is that in fact what you do is assume that it's not, right? It's not belong to it. And you find that actually when you try to, based on the definition of Nash equilibrium, the mass exists, there's other strategy which would be larger than the one that's not. And then from that, you can basically come out with a conclusion. It would conflict with your assumption here, therefore prove that is indeed the case. But visually, you can always see that this is best response curve, and this point always exists there. Therefore, it's a closed graph. So once you have that, and you can basically say complete proof, basically say that indeed there's existence in the finite game. So the Pareto optimality is really say because of the situation as we discussed that not necessarily if you're looking at socially, it's not every is good. So they might have some conflict if you wanna play as a god to looking at the socially, but natural climate not necessarily give you it. So the Pareto optimality is that really to think about this strategy as whether you can improve it, but without harm to others. So if you wish to that, you wish to the Pareto optimality. So this is actually related to this multi-objective optimization as well. And the social optimality is that to really looking at whether the solution you got is indeed socially maximized. In other words, whether they can give a benefit for both of them. So a typical way is just to looking at the summation of the reward of this agent to see whether this solution is a social welfare optimizer. If it is a social welfare optimizer, they also maximize that as an objective. So sometimes that when you looking at the solution, particularly looking at this magnet design solution, can you design the game so that the equilibrium would go in line with the social optimal solution, right? So that's the way you really try to test this out.